And thanks to the UIC Noise and Vibration Work Group for the opportunity to present the project. So I have as content of my presentation, as you see, how the project was created and started, the goal of the project, who is in the project, some statistics, the planning, and then some details about the methodologies we used. And at the very end, already some condensed results. I cannot go in all details about results, but still I have made one slide with an overview of the results. So the project has some history. When I was working at Infrabel around 2013, it was still the era of the rail dampers. I also investigated what is now the effect if we compare different rail paths within the same stiffness range. What is the effect of the difference in the contact surface between the rail path and the rail on track decay rate? And there I've seen there were huge differences. So that was a trigger for analyzing in detail what can be done with the optimization of a rail path. In the meantime, at Infrabel, we already install optimized paths since 2018. But the first proposal I did was in 2014 on one of the meetings in Prague. So we had to wait until Pinar joined UIC. And then the question was not, shall we do the project, but when can we start the project? And okay, then we started with the opt-in process. We had then the kickoff meeting in 21. And so now we have the first results of the project. So the goal is to be pragmatic and based on results of the terrain. And that's why we don't want to make models to see the effect of the rail paths, but we want to measure it together with all the project partners. There are several project partners. We have 12 infra managers. You will see it on the next slide. So we have access to measurements from the terrain with a wide variation of rolling stock, of speeds, of typical rail fastening systems. And so we have the opportunity to compare exactly what is now the effect if we optimize or change the rail path. Also, very important is that we not stay in our bubble as acoustical engineer, but that we also try to get the track engineers on board so that they can, from the beginning of the project, interfere and see how we work. So there is a close collaboration with the train track interaction sector. So here you see all the companies, the rail infra managers who are in the project. And I have put on in yellow blocks the number of optimized paths that are installed and tested during the project. So you can see in total, we have in the project 30 different rail paths that are installed and tested during pass-bys of trains. So we have 12 reference paths that are already the standard in the different countries, and we have added 18 optimized paths installed at 10 sites. The optimized paths, it should be clear, it's not one optimized paths, but the optimized paths who are tested in the different countries, they are designed according to the specifications of the typical countries. So there is not only one optimized path, but they have other stiffnesses, thicknesses, dimensions according to the specifications of the different countries. So here you have an overview of the paths. So today we have data from 8 countries already into the project. So data means the raw data as it is sampled during the measurements. So because in the project, we apply exactly the same processing for all the countries, because you can imagine if you ask different consultants or measurement equips to measure pass-by noise, you can have differences on that level. So that's why we decided we start from the raw data and we apply the same processing for all the countries. So we wait now for final 4 countries to add 3 optimized pads and 4 reference pads. The optimized pads we have tested are provided by 4 different suppliers, as you can see. And the goal is to keep the rail pads as soft as possible, because that's what track engineering wants, but design it in a way to have a high track decay rate. So track decay rate, I think most of you know what it is. It's the amount of damping to the rail vibration. So we want a lot of damping to the rail vibrations so that the rail as a source emits less noise. And that's the goal. And you can see we have different stiffnesses for the optimized pads between 60 and 230 kilonewtons per millimeter. So, and of course they have frequency dependent stiffness and damping that is introduced in the optimization process. So we want more damping in the high frequencies to damp, for example, vibration modes as the pin-pin mode around 1 kilohertz. So we want to add as much damping there as we can, keeping the rail pad as soft as possible. And for some pads, we used finite element optimized design. So meaning that we try to change the distribution of the stiffness over the surface of the rail pad in order to have more effect for specific vibration modes. Here you see the different work packages. I will not read them, so you can see we started with a database, work package 2, which is very important to see what is today installed in the different countries as rail pads. And then work package 3 then was to select rail pads to be tested. You can see within the time frame, the time that was initially foreseen for these activities. But you can see for the measurements, for example, after installation, for the measurement, we needed more time for some countries to be ready to install the pads in the track. And finally, the work package 6 is the most, not the most important, but it's a very important one to have all the information available in the final documents. So in the different work packages, we applied some calculation and analysis modes, let's say. In work package 3 and 6, I will come into detail later. We have developed a software tool that makes it possible for the project participants to compare the results in their country with other countries, and even more, try to do a calculation to go from one railpad that was tested in one country and compare it what could be the result in their country. There is no time to go further in detail on the track separation we tried to apply here. So I will go now straight to the selection of the test sites. So the way we do the measurements, you can see it on the upper figure there. So we instrument 2 sections of 100-meter length, and we install the standard pads, or we compare the standard pads with the optimized pads, and we measure simultaneous the 2 sections for the same train pass-bys. So that's the same approach that is used in the different countries. So here you have 2 different pads that are compared, but in some countries there were 3, or at ÖBB there were even 6 rail pads that were compared. Then for the tests and the selection of the site, we applied the norms at the 3095, and then the norms to measure the track decay rates and the roughness measurements. And of course, if you select the test site, then the question is, do we have for these sites already track decay rate measurements available, roughness measurements available? So that is clear, I think. The practical considerations are also important. So if we select a track, for example, we should verify what are the speeds, what is the rolling stock on these sections. So all these parameters are important to select the site where you do the tests. And then for the equipment, it's standard class 1 equipment that is used at all sites. And additionally, we added that we want exactly the same sensors on the 2 sites where we make the comparison. So to avoid that, we introduce already deviations from the measurement sites. So all this information will be also available in an IRS that will be published based on the procedures we have used in the project. So as I said, today we have data available from 8 countries already. From Banenor, Network Rail, and SNCF, the data will be available soon. And for RFI and ProRail, it was difficult to change paths, to compare paths, but nevertheless, we included their standard path in the project so that they can also compare the performance of their rail path with the other countries. So the results, we will have a main document with all details about the measurement and the processing. So we will have more than 1,000 different train pass-bys, different rolling stock, various speeds, and also different temperatures. And as I already said, we have in total 30 different rail paths with stiffnesses between very soft 60 kilonewton per millimeter until very stiff pads, EVA pads, around 1,000 kilonewton per millimeter. And we will have, as I said already, an IRS that gives a guideline how we can compare if we change something in the track. So it's not specifically for rail pads, but also, for example, if we want to compare on the sleeper pads, we can use this methodology to have a sort of reference how to perform the measurements. And then one of the most interesting results, I think, is a software tool. That's a tool that makes it possible for the project participants to compare their results with the other countries and also do estimations of noise reductions based on the measurement data. So the software tool, as you can see, it is for Windows systems. There are 2 main functions. We can, as I said, compare the measurement data from one country to another, and we can also, or you can also calculate the differences when you change a path from one country to another using the track decay rates that are measured. So here's some screenshots. There is no time to go in detail, but you can see maybe at the top the country, the type of train. You have the track decay rate. Top left, you have the pass-by noise. You have insertion loss. You have the database of all the different track decay rates from the project, and you can select one of these to do estimations, as you see in the middle slide. Or you can compare on the 3rd slide on the right. You can see that you can compare one train with another. So for the results, I had prepared a lot of slides with a lot of details, but there is no time for it. So I just averaged together, as you can see, for I think 7 countries here. So you can see the name of the infrastructure manager, Infrabel, DB, BB, etc. And you can see here in DBA the noise reduction when you compare the different paths. So we have an L and we have optimized. So L is a low stiffness path, as it is indicated on the top. and H is for very stiff rail pads. So we can compare the noise reduction based on the soft rail pads. So the curves in blue gives the noise reduction if we compare an optimized pad with a low stiffness pad, let's say. And there you see that we have always very good noise reductions based on the type of train, based on the speed. We go from, let's say, 1.5 to over 4 dB noise reduction. The two blocks in red, I think these are the most important ones because there we compare very stiff rail pads, so EVA pads. So at SBB and in Portugal, they have a lot of very stiff rail pads as reference. And in these countries, it's very important to have a solution if track engineers decide we want softer rail pads, then it can be the case if you have softer rail pads with lower track decay rate, then suddenly they will have higher noise emissions. So in Portugal, they were very happy to see they want to change their EVA stiff pads to soft pads, and still we can have noise reductions around 2 dB. At SBB, we are around 1 dB. So the good news is, I think, for countries that have stiff pads and want to go softer, they don't have to fear that suddenly they will have higher noise emissions. So that's, I think, very good news. So I forgot to say that these are averages for the complete family of trains measured country by country. But you can imagine that the insertion losses, so the noise reductions, differ with the speed, differ with the rolling stock, differ with the temperature. So it should take too long to go in all these details. I think that we achieved our final goal, that is, if we optimize a rail path, that we can use it as a noise mitigation measure. So the conclusions, we have conclusions in this project. So I think we managed that, we managed to get acoustical and track engineers together to work together and to find a solution for testing on the same way the effect of a rail path change. So we were supported by 12 European rail infrastructure managers. We also tried to motivate and support these managers to install and test optimized paths. And then, as I already said, we have now a common method that will be described in the I or S for future if we want to compare a change in a track. And then, as you all know, noise mitigation measures can be very expensive. Talking about noise barriers or rail dampers, then we go from 200 to 2,000 euros a meter track. A rail pad is a low-cost solution. Optimizing a pad is not a high cost. We estimate today these costs, but that has to be refined later. But we can have already optimized pads by adding 0.5 euro extra a meter track. So that's really a low-cost solution, I think. And as I already said, this is for me a very important conclusion. So for countries that have stiff EVA pads, for example, also ProRail, they have 700 kilonewton per millimeter. If they want to go softer, they don't have to fear that there will be higher noise emission because now we have a solution for that. That is my presentation. Thank you.